So we built a sequence of these machines and this roadmap. We spend a lot of time on each one of these machines. They're actually completely different inside. They're each a from scratch design. So there's the design cycle is really long. So it was like 5 years from the first to the second and 7 years from the second to the third. Um, the So we're not just using the next process node like a cell phone company or whatever. We actually try to learn from a previous machine before we design the next machine from scratch. Um, so there's some decorative pictures on here. An Anton 3 node board. It's got this groovy water cooler on it. You can't see any of the inside of it because it's all covered up with heat sinks. And this is our big 512 node machine that we have in a data center somewhere. There isn't enough electricity in Manhattan to run this. There's the front view with all the doors open. So each one of these is a node card. There's like 128 node cards per rack, so 512 total. And the back of it is even more cool looking because you can see all the wiring in there with the network. So let me spend a couple slides on the architecture of this machine. It's massively parallel. It's specialized to molecular dynamics. So this is the architecture basically on one side. There's a 3D torus of processing nodes. It's a big parallel machine with a 3D torus of nodes. The one that's in PSC has got 64 nodes. So it's a 4 by 4 by 4 torus. And that really means it's a mesh, plus it has end-around connections in each dimension, which exactly matches what you do for chemistry when you're using periodic boundary conditions. You can see the next image to the right and the left. So the wiring is like specialized to this problem. So you take your three-dimensional chemical system and you plant it on these nodes in sort of the obvious way. You divide the atoms up where they would land spatially as if you had divided up among the nodes. So each node is basically one chip or ASIC, application-specific integrated circuit. And this is the thing that we design to do this problem. And the chip has a bunch of processing cores in it and the network. So it's wired directly to its nearest neighbors in each of the 6 principal directions. There's like 4 links in each direction. Each chip is wired to its neighbor. So the chip is basically the whole machine. The rest of the board is like power supplies and controls for this one chip. The chip itself is very parallel. It has 12 rows and up to 24 columns. Kind of cool thing is the columns don't all have to work, which gives you better yield if you can take chips where 1 or 2 columns are bad. And then, okay, so each of the little yellow tiles in here has the main guts of this. So each tile is a mirror image of 2 halves, which has the processing stuff on it. So the PPIM is the particle-particle interaction module. This is a specialized hardware pipeline that does 90% of the work in a molecular dynamics simulation. It's doing all the nearest neighbor interactions for electrostatics or van der Waals computation. And then there's a GC, a geometry core, which is what we call our sort of general purpose processor, and a chunk of SRAM. And there's like 2 halves to this, and they share a bond calculator, which is another piece of specialized hardware, and the network. So the 2 main things to take away from this slide is, 1, it's very parallel. There are a lot of things going on here. If you count up 64 nodes times 12 columns times 12 rows, 24 columns, 2 things, there's 36,000 of these processors all working together simultaneously to compute a time step. And the other thing is it's entirely specialized for this problem. Most of the work is being done in these special purpose hardware, and even the network is specialized to like gather the atoms. The other tile that I'm not talking about has a bunch of specialized stuff to gather the atoms and pass them to the PPIMs within a row and take the results and send them back to the GCs. So it's all specialized. It only does this one thing. So I wanted to hammer on that just a little more. This is from scratch hardware for molecular dynamics, built out of hardware pipelines, embedded processors. It's not a GPU, it's not an FPGA, it's not an x86, it doesn't use an InfiniBand network. It's not anything that you program by hand. there's no operating system. There isn't even any virtual memory, so that your chemical system has to fit in all the little SRAMs on the chip in the machine. That sets the size of chemical system um, that you can simulate. There's no backing store that for a bigger system to be multiplexed onto the machine. So the whole machine looks like a big coprocessor in the bad old batch style processing. You load a system on there, it runs for a while, producing trajectory frames, and then you unload it to give somebody else a chance. And this is somewhat automated, so it's like doing a chunk of your time every couple of hours. Because the flip side of this that people always ask is if you're going to specialize in hardware, why didn't you specialize all the hardware? Why embed processors? Are you people cowards? And the answer, of course, is yes. You have to have a hedge against, well, we do develop new algorithms, but also bugs that have to be fixed up by the processors. There's also like lots of housekeeping tasks that you maybe don't think of, like maintaining the distribution of atoms to nodes is heinously complicated. And these GCs have to work together as a parallel program to maintain that from time step to time step. I mean, that like task alone has probably taken a person year of development work that gets refined iteratively, because we only ever write like one program for this machine. So instead of being a company that writes lots of little programs, we write one program and then we tune it until you can't tune it anymore. So that's a good lead into performance. So here's a classic performance slide. So I've got microseconds per day on the y-axis, and then number of atoms on the x-axis. Higher is better. So the Anton 3 RFP had 5 data points in there, and I've plotted them on here to as an illustration. So there's so if you pick one of these, like STMV, the well-known benchmark is a little over 1 million atoms, and it gets a little over 40 microseconds a day on this machine. This is kind of, you should view this as an upper bound, basically, at least initially. These are globular proteins, so they're easier than like membranes. It's running NVT, so it's not paying for the barostat yet. And any features that you enable will have some cost. So this really is no deeper than the 5x, the table of 5 benchmarks that are in the RFP, except that plots are like way more fun. So I can decorate this plot. And that's what I'm going to do over the next few slides. So the first thing I want to say is the RFP describes the range of systems that are appropriate for this machine as about 250K atoms up to 8.5 million atoms. But there's really a sweet spot where you get best efficiency if you keep it between like 500K and 6 million, or maybe even tighter than that. You can see that this line is not a perfect 10 dB per decade kind of slope. There's a little bulge in the middle, and that's real. It's just better at systems that are in this size. On the low end, it's slowing down because there aren't enough atoms to keep all these nodes busy. And on the high end, it's running out of memory. The closer you get to the memory limit, the more devious and horrible tricks we have to play to make things fit into that SRAM. Like we start double pumping data in a certain data structure in the PPIM. Anyway, I could talk about that forever. All that SRAM is shared with the extra features. So if you have a thing, you can't run the maximum number of atoms and turn on very many extra features. Like if you're expecting to do enhanced sampling, that costs memory. So you really want to be in the sweet spot. The other way I could decorate this is I could show the Anton 2, the 128 node Anton 2 had less of a bulge in the middle of the ground. Compared Anton 2 to Anton 3, it's either 10x faster on the same size system. This is an ATPAYS simulation. It's about 300,000 atoms. You could run it at least 10 times faster on Anton 3, or you can run about the same speed, but run a thing that's 10 times bigger. And I'm actually being conservative here. These really are 10x rulers on my log plot here. So it's clearly more than 10x and more than 10x in that direction. But when you get to say 10x, how can you resist? let's see. All right, the other thing I wanted to put up here was, or wanted to decorate my plot with, is I can decorate it with actual example runs from both inside DesRes and PSC. So these are samples taken from a database of, we do performance analysis on all the runs. So the green circles here are DesRes runs on a 128 node Anton 2 or a 64 node Anton 3. And then the purple diamonds are the PSC numbers from the last couple of years. And there's several things you ought to take from this plot. First of all, it really illustrates that there's a lot of variance in performance. I mean, the RFP numbers are just a guide, but there's, I don't know, this is varying by almost a factor of 2 from the bottom to the top. On Anton 2, some of these are above the line because the Anton 2 RFP, we gave numbers from 2016 and then never changed them because we didn't feel like it, but the software got better. In Anton 3, it's pretty much a strictly upper bound. Maybe the software will get better, maybe. There's some really stinky performance numbers in here. So these are PSC systems that actually ran very slowly. And I actually looked at this I've always speculated before, but I just looked at one of these simulations. And in fact, yeah, it's set to output trajectory frames every 2 picoseconds, which is at least 100 times more often than normal. So this thing is running at the speed of the IO system instead of the speed of the machine. And then the last thing that comes out of this is obviously I don't have any purple diamonds on this because we haven't given you the machine yet. And am I nervous about that? Yes. I have no idea what you're going to do with my machine. Even the numbers we have are kind of sparse. This is a very big machine. This is like the biggest machine that we ordinarily use. That the 512 node Anton 3 is kind of for special occasions. So the 64 node is the biggest one that we light up on most of the time. So you're treading in new territory here. Come back next year and we'll put purple dots on the right-hand side. And the last thing I can do is I can take those two curves now that are sort of cartoonish straight lines and put them in the performance universe of all the rest of the machines that we know about, where the best machines in the world are the Anton 3. This is like the no holds barred version of how much performance you can get on molecular dynamics. The fastest machine is either a 64 node machine Anton 2. This is actually the rest of that line. 64 node machine if it's a small number of atoms, or the 512 node machine for a large number of atoms. And we can see the old numbers for Anton 2 and Anton 1. And then everybody else. And everybody else falls into two categories. There's either GPUs, which kind of follow the curve for one GPU. The black dots in here, or the black triangle thingies, are the NVIDIA H100 numbers that we ran recently using Desmond, our other thing. And then the red numbers are anybody else we could find. Basically, GPUs haven't yet figured out how to get any speed up over one GPU. So there's some 4 and 8 node GPU numbers in here, but they're no faster than the H100. So they're at this line, and it's basically as fast as one GPU can run, and it gets faster with each generation. But on a log plot, that's only like 1.5 or 2x faster on each generation. It's going to take them a while. And then the other kinds of machines in the universe are supercomputers like Summit, which are really also using GPUs, but they're using an awful lot of them connected by some general purpose network like InfiniBand. And they can run very large things. This actually goes all the way out to 1 billion, I think. But for speed, they kind of stink. They run at the speed of their network, which looks like it's about 200 nanoseconds per day, and probably getting worse with each generation because their networks are optimized for high throughput of large packets, and our network is the complete opposite. It's optimized for tiny packets because it's specialized for molecular dynamics. And that is it for me, other than this cool picture of the Anton 3 chip in its case. You ready, Avi?
Sure am, Ken. All right.
Thank you, Ken.
Then we'll take questions when Avi's done.
So Ken set that up. And I'm going to talk a little bit about the enhanced sampling stuff. And Parker is sort of I'm a software engineer mostly. Parker's here as the chemist to jump in if anyone has questions about like the actual chemistry implications that I can't answer. Or also to jump in if I say something that doesn't seem quite right. So feel free to do that if you like Parker. Um, so Anton is super fast for straight up direct MD, and that's most of what Ken was showing and presenting there. It also has some accommodations for if you want to get more than you can get from just running regular straight MD. And we developed an algorithm in-house called time-square sampling to do enhanced sampling on Anton.
The transition state structure.
And
Looks like Avi's breaking up a bit here.
square sampling, it has nothing to do with the square of time. People always ask about that. It's just called that because our offices are near Times Square. And Christy Prodescu, who is the main developer on it, thought it was neat. A neat callback to like Metropolis or other metrics and algorithms. So it has built-in online free energy estimators. Usually when you're doing various kinds of enhanced sampling, like simulated tempering, you need to find some way to pre-estimate the enhanced sampling at each, say, temperature or Hamiltonian that you're working with. Time-square sampling does this online automatically for you. And it uses them sort of like if your energy landscape is something like you have down here in the left corner, you've got like one energy well down here, a higher energy well up there. But if you just simulate at a low temperature, it's going to be a very long time before you cross from one well to the next. So with enhanced sampling, using TSS or anything else, you jump around in terms of what set of simulation conditions you're using. In this case, moving to a higher temperature. And at that temperature, the effective energy barrier is lower, so you can cross back and forth between the two wells, and then have the ability to go back to the lower temperature parameters and still be in that other energy well at that temperature. So it lets you explore in a balanced way the different energy wells in a way that you could, even though there's a high barrier that you can't easily cross at the sort of default Hamiltonian. Another technique that we offer the ability to use is something called tempered binding. And we published this in PNAS in 2019. And this is mostly for protein-protein interactions. And the way it works is you can think of the two proteins as having lots of pairwise interactions between the pairs of atoms. And tempered binding says, okay, you have your default set of parameters, set of conditions where you have your van der Waals, epsilon, and sigma having certain like physical parameters. But let's say we want to run the simulation, come together and then come apart really easily, so that you can both explore like the true physics of it, but also something that will let you find new poses, not just get stuck in one that you happen to encounter first. So we have this sort of lambda ladder, and lambda 0 is the physical parameters. Lambda n is parameters that are geared towards the proteins not wanting to associate with each other. Basically, you're increasing sigma so that the sort of natural comfortable distance for two atoms is further apart than they would normally be, and reducing epsilon so they don't tend to stick together very much. And then when you run these simulations, you can see that your lambda over time goes up and down because you're exploring sort of the physical conformation, spending some time in sort of something that's equivalent in a sense to high temperature, but more targeted, and then coming back down in different conformations. And I'll show you a video of what can happen when you do this kind of thing, and how this lets you escape these sort of metastable traps that I was alluding to. So this is a simulation of Barnes and Barstar interacting. In conventional MD, they bounce around for a bit and then they find a pose. And you can see the time scale on the top left. This is quite long. We're getting sort of to the almost 100 and above 100 microsecond time scale, and it's just sort of hanging out there. But if you compare it to the crystal structure in gray here, you can see this actually isn't the crystal structure pose. It's not really the one you were wanting to find. If you instead use this tempered binding approach, which you have here in red. And I'm not showing the lambda ladder, but you can see it sort of like forming transient associations, and then coming back into a more stable pose. And we're at 16 microseconds here, so a lot shorter. And this did find the crystal pose. And if you kept running a temper binding simulation longer, you are going to see like a lot of it's going to come into such a pose and it's going to disassociate, and you should get to explore multiple binding and unbinding events. So this is not just it finds it once and it hangs out there. And something I think I didn't mention on an earlier slide is this doesn't require the crystal structure as input. Like this is just changing the dynamics of the interaction of two proteins. This doesn't know anything about the interface sort of up front. So this can actually help you find correct binding poses potentially for proteins where you don't have a crystal structure. So, okay, I've talked a little bit about simulated tempering, which is the temperature tempering, where it's also figuring out the free energies on the fly, so you don't have to supply them. That's the adaptive weighting that we're talking about here. There's tempered binding. We also support applying restraints between centers of mass and groups of atoms. So if you wanted to, for instance, have something pulled in and out of a ligand pulled in and out of a pocket, you can actually set up a tempering schedule where the distance between the pocket atoms and the ligand is something that you control with TSS. And that could let you figure out things like the free energy of binding. We also support conformational restraints for the RMSD to some target structure for a group of atoms. And that could be something like, let's say you have a protein loop that you know can sample two different conformations, and you could have a restraint to one of the loop conformations as your initial sort of rung in TSS, and then say, okay, along the course of our TSS schedule, we want to increase the distance to that conformation, and then have the other loop conformation as the other end of the schedule, decrease the distance to that conformation, and that could let you explore loop transitions. And these things can either be controlled by TSS, or you can actually just set a schedule. So if you want to do like non-equilibrium sampling, where you pull something out of a pocket one step after another at points in time, that is also available. I'm going to talk a little bit about sort of some of the viewing software we have to analyze runs of these sorts. And there's a link at the bottom. This is the link for the Anton 2 version of this documentation at PSC. We don't have the path to the Anton 3 version yet. It'll, however, be very similar to the Anton 2 software. And I'm sure that PSC will update you guys once they have something. Okay, so when you're running this analysis, the command is at the top. You do this pytss psc plot basic, and give it the path to your working directory. And you get these 4 plots here. The top 2 plots are showing you how it's exploring the different lambda values, or rungs, as we call them, in the ladder. The top left plot is a histogram of, for a given rung, how much time it's spent there versus this red line, which is the target for how much time it should spend there. Because you'll see that if you run simulations that are doing something, a big discrepancy, blue histogram and the red line, probably your simulation is not behaving well or hasn't yet sampled enough time. What you're seeing here is pretty acceptable. It's okay for it to be noisy. You just don't want it to be like all the sort of histogram mass to the left where the line should be flat. Similarly, on the top right, this is showing the distribution of rung visits over time. If you see it sort of like a dense pattern, that's good. If you see it spending a lot of time sort of in one chunk of the graph and then spending a bunch of time in another, you may have something that's not well converged. Bottom left plot is the free energy with respect to rung at the final time. And the bottom right plot is the difference between the 2 end rungs, the free energy difference estimate as a function of time. And the shaded in blue is the error bars for that. And that can give you a sense of how well converged you are. And if you see something that's sort of like coming in nicely, that's probably doing pretty well. If it's jumping around a lot, not so much. And that's the last thing I have in terms of the slides. Got a survey link here, although I think they're also going to post it in the chat. But yeah, I think we're prepared to take questions.
Lots of time for questions.
Great. I just drank a lot of coffee before this, and I'm not used to that, so I may have gone faster than usual. I apologize.
Oh, you're about as fast as you usually are.
I had such a good excuse, Ken. Why do you got to take this away from me? Anyway.
Okay, I'll ask a question. So since the Anton runs are supposed to be an hour long, are these enhanced samplings designed to get finished in an hour, or can they cross over multiple
Oh,
hours?
I'm sorry, I misspoke that. It does it in hour-long chunks, but your simulation can be as long as it needs to be. It can be days. It just gets multiplexed at about an hour or 2 hour granularity. Make sense?
But I know that, but I'm curious if these enhanced samplings, do they get a do they save all the stuff to cross over multiple?
All the runs do. Like we're
Okay.
running, yeah, like any kind of Anton run can be broken up across multiple segments with no difference than if you'd run it straight through.
Okay. Thanks.
Hi, this is Lena. I have a question, probably for RV. So we found that, I found personally that writing Anton proposal for enhanced sampling is quite challenging. The reason is because if we use TSS, we have to tune the parameter for number of run. We have to tune the parameter for scaling, and do we scale charge, or we scale charge of van der Waals? All of that tuning has to be factored in when we write a proposal. And sometimes we could end up using half of the allocation just to tune the parameters, right? And so do you have any suggestion how to write proposal using enhanced sampling method? And also another suggestion is, we can get the plot that you just showed when to check the sampling from the TSS. But sometimes, the sampling is not good, and we don't find enough information for troubleshooting to find out, okay, if we, something didn't converge, what parameter should we tune and to better utilize our allocation? So anything, if more documentation for post-analysis, troubleshooting will be very useful. So any suggestion?
Yep. So the first thought in that is that for TSS in general, you should err on the side of having more rungs rather than fewer. The adaptive allocation of the number, basically, it weights things such that it shouldn't, like you can overdo it. Like it's possible if you go to like tens of thousands of rungs, you might have trouble. But on the
Oh
whole,
yeah.
if you, yes. So as Ken says, don't go too crazy. But in general, the way the TSS algorithm is built, unlike like REMD or something like that, having more rungs will not hurt you. It will just spend less time at each rung. So up to reasonable limits, more is very reasonable. That can help you not have to worry about like exactly where you're placing the rungs or things like that. In terms of difficulty with like debugging particular choices of parameter schedules, we have those problems too. It's not that straightforward, unfortunately. For the protein stuff, the things that are used in the PNAS paper are not bad choices. But for more exotic things, unfortunately, it does just have to be like developed and figured out. I don't have really great suggestions there. Yeah, I don't have really great suggestions there. Parker, do you have any thoughts on that?
No, so generally what I would recommend is try to find umbrella sampling papers that are similar to what you're trying to propose here and try to study their rung structure, because typically there's a lot of thought into like how many rungs, but also how you're going to, how the rungs actually overlap one another in the energy landscape or the energy space or something like that. So I would recommend trying to see if anyone's done anything and try to start with I would recommend potentially starting with a similar construction. But definitely, as Abhi said, this will require some trial and error on your part. But as they've noted, and internally, I use TSS for my own applications. More is generally better, right? So if you're deciding between like 200 or 400 rungs, like err on the 400 rungs. Don't go to 10,000, like Ken said, but to try to ensure that there's sufficient overlap in your window.
Okay, so 200 to 400 is a lot. That was what I was waiting for because 10,000 freaks me out. I get the tickets from you guys.
But 200, 400 is fine.
200 to 400 is like a lot and fine. Cool. Thanks. So actually, there's some questions in the chat. Maybe we should take the questions in the chat before we take more from the audio. So one was from Valentina. What about the speed of smaller systems from 180 to 200,000 atoms, or is it? Or do system size get taken into account when during the evaluation of the proposals? You can probably guess what the smaller systems are going to look like from that last slide that I gave that interpolated between our paper and the RFP.
But they'll all run, just as Ken said, as you get sort of lower, you start to lose efficiency because there's not enough atoms to actually keep everything busy. So that's the main purpose of having that window of atom sizes in the RFP for what we're looking for.
Okay, so if I can MC here, so the next two questions are about membrane, using enhanced sampling protocols on membrane proteins and tempered binding on membrane proteins. I think one of the papers on tempered binding did use a membrane protein.
Yeah, we've definitely done stuff of that. There was also a question about what is the cost of enhanced sampling? Like how much does TSS slow stuff down?
What's
But
your answer to that?
Actually, it shouldn't slow it down too much. If you're doing single, well, it depends. Yeah, I'm gonna guess like 10 or 20%. What would you say? Like all
Oh,
things being equal?
what I've observed is chemists will like crank up the enhanced sampling until it slows down by 2x, and then they'll stop, right? Because that's the rational thing to do. If you think your enhanced sampling is speeding up your simulation, then you'll keep piling it on until you get to 2x slower, and then you'll file a ticket.
That's fair, yeah. But so yeah, so I'm gonna say
Less than
that's fair.
2x, less than 2x. Do you
There's the
accept
question about
periodic
Yes.
boxes that are 10 to 20 times larger in one direction? What's the upper bound on the aspect ratio for this machine? It's a lot less whack than Anton 2 was. I'm not sure I've tried something
Is that
that's,
in our RFP? Did we mention that in the RFP, Ken, or is it?
I don't remember. Do we?
We
Yeah.
just say minimum size 50 angstroms on each side, and then to email us if one of the dimensions is larger than the others. But we don't say.
So it's a good question.
It is a good question. I'm not sure I've tried aspect ratios as high as 20x. You should follow up an email with Marcella.
Yeah, if it's going to be that much bigger in one dimension than the other, definitely email us. But it sounds like, Ken, that's like 2x, things like this you think shouldn't be.
2x are no problem. 3x, 4x is not a problem on Anton 3. It's way better about this than Anton 2 was.
Okay.
I mean, one of the issues is that these run for so long that your protein rotates, right? So yeah, that's a lot of times you end up with a big square box or big cubical box to let your protein rotate. But if it's fixed in some orientation because it has a membrane.
There's a question about
Go ahead.
if you're thinking, go ahead.
Oh, I'm done.
Okay. There's the question about whether tempered binding would work for interactions between two membrane proteins. I bet it would, yeah. I don't know if we've tried it, but everything about the way it works should be well behaved there, I think. Parker, if you have any thoughts on that.
No, I think it definitely should. Yeah, I mean, I think I've done something similar actually internally, so I think you should be able to do that.
Cool. Protein nucleic acid interactions. My guess is you'd have to play with the parameters. The current, like the sort of default parameters are basically set up for protein interactions. Conceptually, yes, I think it should work. But it's a question about post-simulation trajectory handling.
Oh yeah, what are you going to do with wicked huge trajectories, Bill?
We are planning on suggesting benches 2 for analyzing the trajectories instead of Coleman. But we haven't looked at the tools yet. Besides the usual. We do have tools with VMD to decrease the size of the systems, remove waters, things like that.
And
Right.
then the second half of the question was about equilibration. And with extreme trepidation, I will admit that Anton 3 can do equilibration. It's just that that's like the first time that the rubber hits the road. If you've like messed with your force field parameters and you throw it into our equilibration, you're going to get some horrible Anton error that tells you nothing, when it's really going to be the fault of your parameters. So I have to think that you need some other way to equilibrate just to test things.
And so maybe this is something we can talk a little bit more about and provide some more guidance. But when you say Anton 3 can do equilibration, then maybe that suggests that folks at least don't need quite as much equilibration as they did before. But some
Yeah, you want to like show that things will like get to where to run a couple of time steps in some other tool that gives sensible error messages. But then if you have to equilibrate things 5 more times, you could do it in Anton. At least
Right.
that's what I'm envisioning.
Right. So it sounds like that we could push it back. So you can the fact that you can run these really huge systems now, we can help you out because if you don't have to equilibrate on other hardware for as long. So again, this is I think we'll follow up. Maybe we can give some recommendations there, for those that we can add to. I don't know. Maybe we should add this to the RFP in case people are thinking about these kind of questions for how much time should I ask for, kind of questions in the proposal. But then some of the stuff will be fine tuned as people actually get on the system and try it out with all the different things we'll see that we're excited to see from the community.
Let me jump on the metadynamics question that Martin asked, and I see Parker replied to a little bit. It depends a little bit on what kind of metadynamics you're trying to do, because metadynamics is about filling in energy wells with respect to a reaction coordinate. If it's a reaction coordinate that we support, you can use our enhanced sampling with like basically umbrella sampling. If you can like, I think you can do that. Yes. Yeah, you should be able to, like, if you can express your the reaction coordinate that you would normally be doing metadynamics on as something like a distance between pairs of groups of atoms, then yes, we can do that. If it's something that isn't expressible in the things that we talked about on that slide of the 4 kinds of things we can do, no, we can't do it.
Cool, thanks. I think the next question I see is for in-person Zoom training. Yes,
Yeah, I
there's
was
going to
just
be one.
answering that. Yes, we will have our usual getting started seminar after the proposals are approved. And so I will talk in my next talk, I will talk about these dates. We are targeting March to begin running on Anton for the allocations to begin. And so immediately after, we will offer a getting started seminar or workshop.
Yep. But as in the past, that'll be just for folks who were allocated time on Anton. So that'll be folks who have so they've been allocated time. You'll actually get on the system. We'll help you get up and running. At that point, it's not going to be something open for anyone to come and bring. We just don't have the resources to support that.
Mm-hmm.
And will it be in person this time? COVID's over.
We haven't thought about in person. What's that? No,
It's so much better in person. It's like an escape room. We all get stuck together and you can't leave until your system runs on Anton.
All right, Ken wants an excuse to come to Pittsburgh.
Think about
Noted. We'll decide.
Recommendations for software for preparing million atom systems. Desmond on an H100 works great.
Well, Ken's suggestion. So Ken, let me elaborate a little bit there. For those of you who have run on one of the Anton systems before, you know that there's a process of converting. If you're using NAMD or GROMACS or Amber or one of these other programs not written by DSHA research, then there's a conversion process to get your files into a state where you can then run on Anton 3. And sometimes that can be a challenge. That's that's not, sometimes it's straightforward. We have tools to help, but sometimes it's not straightforward. So if you start your simulations and run them in Desmond, which is the tool written by DSHA research, but it's a standard MD software package, then it should go right onto Anton without any conversion necessary. So anyway, so that's so Ken suggests a beefy GPU with Desmond is a great place if you're starting with a new system to equilibrate, prepare it for Anton. That may not be practical for everybody, but
Yeah, it's a problem.
There are resources at Pittsburgh Supercomputing Center we make available. We have a fair number of GPUs here on our resources. That would have the benefit of you have files here locally that you can move over pretty quickly to Anton 3 if you get an allocation there. And if not, then you can keep using our supercomputing resources for your research and keep applying for the Anton Award for future rounds. So that's I certainly we would love to support anyone who needs additional computing power to do the equilibration preparation for this, or also the post analysis and such using the supercomputing systems at PSC. Our current one is called Bridges 2, and you can find out more about that at psc.edu or on our website. We don't have, well, I think we are getting H100s actually in the not too distant future. So we don't currently have H100s, but we have a lot of A100s and yeah. So anyway, but there will be H100s coming, I believe, as I said, not too long.
Avi, the next question looks TSS-ish. How do we know what
It
lambda
is, I'm
max?
sort of typing in the chat.
Oh,
So the question was basically benchmarks for how fast you could estimate free energy differences for protein small molecule or protein-protein pairs via time square sampling. And for protein-protein, I'm going to guess at least 10 microsecond timescale. Parker, any thoughts on that? Maybe 10 to 100?
10 to 100, definitely going to depend on how large your system is and how large the source space is. Like bar star we showed is like a pretty nice example because the total area is quite small. But as your search space increases, such will your need for more time.
Yep. And protein small molecule is not something we've usually done with these approaches. So I'm not really sure there. I wouldn't necessarily expect straightforward tempered binding to work for that. And if you wanted to do something like Jarzynski polling with like a distance restraint with a schedule, it could be quite fast. It wouldn't be using TSS, and you need to figure out what protocol you'd want to use for that. So yeah, I'm not entirely sure there.
Is the next question, how do you manage the huge data to store? I think that's the next one then. So, we've been talking with our colleagues here at DSHA Research and how they've been handling that. And so there's a lot of things that you can do to not generate unnecessary data or data that you really don't need or are going to use. And so there's a bunch of recommendations that we'll have in terms of what you actually capture when you output your trajectory data. And so I think we're going to be counting on folks to be really good citizens with generating only the amount of data that you need. That also has the benefit of not slowing down your simulations terribly. Like you saw, you don't want to be those 2 points on Ken's graph.
You'll see them next year.
That's right. That's the wall of shame right there. So we'll be creating some recommendations, or we'll be passing on some recommendations for how to capture the right amount of data and not go overboard with this this monster system. And then otherwise we will have but for the data that is generated, so that's the first thing is let's only generate what we need. But the second thing will be We'll have a very large file system there to capture and store the data that's generated by the groups. We are actually committed to keep that. So those data we will keep for the foreseeable future. And also, we're going to help folks, especially the NIH-funded folks, to keep their commitments to NIH that everyone makes to share their data at some point. And so, we'll be working with folks to help make those data available from PSC. So what this means is hopefully, if now we're still working through some things with NIH and on what they're going to actually support us to do on this front. But what we would like to do is make all these trajectories available to the community obviously after you've published your paper in some reasonable amount of time. So usually we give, I think currently on Anton 2, our policy is that up to a year. Well, we give people up to a year to publish. We always talk to people first before we put anything out there, though. But we really want to encourage sort of rapid release of data. That's a great friendly thing to do whenever possible. So anyway, so we're going to try to make the data available publicly from our system for data sharing purposes and maintain it all there. And so we will manage the data. Basically, you'll have the big data store there, and it'll be close to the PSC supercomputer, so you can analyze your data on the supercomputer if you want. You can also decide you want to bring it back home, and you're totally free to do that. But we'll keep a copy at PSC and make that available in some reasonable time frame to the broader community, assuming NIH provides the funding that we need to do all that in some reasonable way. So hopefully I hit some aspect of that question, or all aspects. Okay, so who's next?
What's the typical sampling frequency for your benchmark simulations? Probably like a nanosecond. You mean like how often I write a frame? It's probably a nanosecond.
There's tools on Anton, I think, to filter like by atom type and so forth as you output the trajectories. Am I remembering that right?
Yes.
Yes, there's ordinarily you write out only like not the non-waters and then write the whole trajectory every 20 nanoseconds or something just for reference.
Yeah, so for people who are studying, really want the wider interactions, then yeah, it's gonna, you don't have as many knobs, but there's basically not a lot of knobs there you can turn to limit how much you're writing out, and we will encourage people to use those wherever possible.
Hey, the bell is about to go off.
Yes.
Let's see, I'm just scrolling through the chat. Did we get through all the questions?
There's one more. That I don't understand.
The last one. Yeah, so they have a structure which is mid-resolution taken from cryo-EM that has 6 million atoms. That seems like a good application to me. And we encourage new users without Anton experience.
They're basically asking if they can relax the system into a good final confirmation. Sounds like, I mean, you could get Parker, maybe you've run like DNA RNA systems, I guess. If you had something that was like close, do you think you could use Anton simulation to basically relax it down to a decent, reasonably likely structure?
So the difficulty here is going to be, you're going to be kind of moving from like a 20-30 angstrom, which is kind of, I don't want to say blobology, but at that point it's kind of blobology. You have a rough idea. So the ability to relax using Anton is going to be very dependent on your ability to get atom per atom placement, right? Because inside of MD, you have to explicitly place every single atom, all the backbones, all the side chains, all the protons. And oftentimes you're not going to see that data coming from cryo-EM. If you're building it in a way such that you're using homology modeling to basically fill in the blobs, that might be a good start. But you're definitely going to need to be careful about your initial placements, right? So if you have like two protein domains that are overlapping each other or something like that, you're going to have to ensure that they're not clashing and other things like that. So there definitely are some caveats here. That being another thing I want to say too is I know Anton, I'm pretty sure Anton cannot do this, but I know there is a method that I've seen. I think it's in NAMD or something like that, where actually you can do some sort of restraints or some sort of MD that's fit to a density. But this is probably way too big for that. Yeah, with many caveats, I say you could definitely run the MD, but you're really going to have to be careful in how you use that data coming out of it, simply because you're going from a very low resolution or mid resolution to atomic resolution in terms of the simulations you're running.
Thank
Yeah.
you.
So maybe first build the system on another machine until they have a better resolution, and then go to Anton.
So it's 3 o'clock. Do we go to a different Zoom at 3 o'clock, or
Yes.
how does this work?
Please. Yeah, because yeah.
Okay. So we're all right. So we're going to move over to the next webinar. We thank you all for joining us, and thanks also especially to the RD Shaw Research folks here who gave us such a great intro to Anton 3 and answered a bunch of questions. Feel free to email, follow up with other questions we didn't quite get to in this session, and we'll be happy to answer those and get answers from D. Shaw folks when we can't answer them directly. So thank you all. Take care, and we'll hopefully
See you for the next talk then.
Thank you.
Bye.